Hi class, good morning. Welcome to the continuation of our lectures on electrodynamics. And again, our reference for this lecture is the Introduction to Electrodynamics by David J. Griffiths. And I recommend you that get a hold of this book. It's really worth it. So today, um, let me just adjust everything. So today we will be dealing with work and energy in electrostatics. So let's look at this scenario. Suppose there is a stationary configuration of source charges. You have this configuration of charges, this one. And then you have a test charge Q that's placed here. And then you move this Q to point B. What have we learned about electric field? Electric field is a conservative field. So whatever path you go through A to B, it doesn't matter because it's path independent. So you have that. So the question is, what is the work done when you move the charge from A to B? Let's take a look. So the electric force that the Q experiences is always F equals QE, because the Q, the capital Q here, will feel the total electric field that the charge distribution is affecting it. So the charge will feel a force that's QE. You can review this formula in the first lecture of this chapter. So the force that must be exerted by Q must be opposite to the force that the distribution acts on Q. So the Q will have this force, and that this force will be replaced here because it's the work done by Q, and the Q exerts a force that is negative Q times the electric field. Remember that the electric field here has a direction, and so the work, as this is the definition of work from classical mechanics, but then work can be but then the force of the work can be replaced by negative QE, where Q is a constant. The test charge is a constant charge Q. You can take that out of the integral here, and then you only integrate E dot dl. So Q, but what is E dot dl? Previously it is just the E dot dl from point A to B, is just the potential difference of the 2 points. So this is just VB minus VA. We learned that in the previous lecture. So note that the electrostatic force is conservative. So it doesn't matter which path you will take in going from A to B. So if you divide the work done by Q then you will have the potential difference to be equal to the work done per coulomb, per unit charge, I mean. So now here's the catch here. So your work is equal to Q times, so for example, you are going from uh, infinity, which is very far away, to a point where it is r distance from the origin. So your work will be this. Your work will be this. But at infinity, you know that if you take the reference point as to be at infinity, so at infinity, this v will approach to 0 or becomes 0 at infinity, because you're already very far from the distribution of charge, and the r there is so large, and the electric field, which is 1 over r squared in proportion to the distance from the point to the distribution of charge. So if r 1 over r square is so large that becomes 0. Or for the potential is proportional to 1 over r. So if your r is so large, 1 over r would be also 0. So you're now left with this one. This. So your work now will just be equal to Q times the potential at point R. So suppose we assemble charges. So like for example, we assemble 8 charges. First, it's not possible for us to, well, it is possible for us to take 8 charges simultaneously, but for us to be able to calculate the work, we assemble a charge one by one. So how much work would it take to assemble the entire collection of point charges for the 8 charges, for example? So we try to bring one charge first. Say we bring Q1 here, Q1 at this point, and then from infinity we bring Q2. So we bring Q2. From infinity we bring Q3. How much work is done? So first, let's calculate the work done on the first charge. The work done on the first charge. Here, for the first charge, there is no other charge that it is going to interact with. So there's no electric field that will act on the first charge. So therefore, because work is Q times integral of electric field dl, and your electric field is 0, so the force there would be 0, and then the work will also be 0, because work is equal to the integral of force time that dl. Now you bring in charge 2. So here, from here, so you don't have any charge at first, then you bring in Q1, and then now you bring Q2. Will there be work done there? Yes, of course, because Q2 will now experience the electric field coming from Q1. So what is the electric field that's felt by Q2? or what is the electric potential in that case experienced by Q2 from Q1. So the potential is actually equal to wait, the potential V is equal to 1 over 4 pi epsilon sub O Q1 over R, the distance between R1 and R2, R, and you multiply this with Q2 and then you multiply this with Q2, and so that you will have this as your work, and so you have this expression. So the work that is done in bringing charge Q2 in the presence of Q1 will be 1 over 4 pi epsilon sub O Q2 times Q1 over R12. Of course, R12 here is the distance between Q1 and Q2. So let's go now. If we take another charge Q3, there, so what happens is that Q3 will experience an electric field from Q1, so there's work done by the force that the Q3 exerts on Q1, and also, since there is also the presence of Q2 there, Q3 will also have to do work on Q2. So you have to add these two. So again, work is not a vector quantity, and electric potential is not a vector quantity, so you can just add them immediately. So this is the potential felt by Q3 on Q1. This is the potential felt by Q3 on Q1. If you multiply that to Q3, that's the work done by Q3. And then this is the potential experienced by Q3 on Q2. Experienced by Q3 from Q2. And so the work done there is, if you multiply Q3 to that quantity and then you add, that's the total work. So you have to take note that this is the distance between Q1 and Q3, and this is the distance between Q2 and Q3. So similarly, if you take in the fourth charge Q4, then the work done would be this expression. So you have 1 over 4 pi epsilon Q4. The work done on Q1, you just multiply Q1 over R14, which is the distance between Q1 and Q4. And then you have Q2 also, and then you have to know the distance between Q2 and Q4, and then Q3 also, you have to know the distance between Q3 and Q4. So so that you can calculate the work done in assembling 4 charges. So, but if you add all the works, like the total work done on Q1, Q2, work done by Q1, Q2, Q3, you just have to add W1 plus W2 plus W3 plus W4, and so on, if you have so much more charges. So So for the first four charges, your work will just be this expression. So you just add them all. Look at this. You have Q1, Q2, Q1, Q3. This is Q1, Q2, Q1, Q3, Q1, Q4, Q1, Q2, Q3, Q2, Q4, or Q3, Q4. And yeah, the corresponding distance between the two charges. And in this case, you have you notice that there is no repetition, like there's no Q3 Q2 because Q2 Q3 is already here. There's no Q4 Q2 because Q4 Q2 Q4 is already here. There's no Q4 Q1 because Q1 Q4 is already there. So you don't repeat the order. So that's the rule in taking or in calculating the work done in assembling four charges. So what if so what if you are bringing in a lot of charges, say n charges? So your work will be this expression. So that's the work. That's the work that that you can you'll be able to do if you assemble n charges. So here you have n going from 1 to n. The j, I mean, j going from 1 to n. But take note here, there's another condition that j should be greater than I. Just like here. Just like here. This expression. So, but you can actually rewrite this expression to this one. But of course, oh wait, that's the same expression. You can actually rewrite that into this expression, this one here, where 1/2, you take 1/2 out, you have to multiply by 2 and divided by 1/2, because in this expression you will count, for example, Q1 Q4 and Q4 Q1 at the same time here. So this is just an equivalent. These two are just equivalent. They are just equivalent. So anyway, let's expand that so that you can see the expression. So that's the work done. So look at this. If you compare this one here and here, Qi will just be the charge that you bring. first you bring Q1, then you bring Q2, Q3, Q4, and so on. And as you bring in the charge, you will feel different potential. The potential is changing because there is the presence of charge. When you take in another charge, you add up the potential of that charge, and then when you bring in another charge, there's a new potential that the new charge will feel because of the addition of charge as you bring in the charge. So you have now this is for discrete distribution. This is for discrete distribution. So how about for continuous distribution? What happens? So here you have so that's in the other slide. So here well, of course you can read the text here and then you just do some readings. So there are problems here that you can solve. Problem 2.31. You bring in 4 charges, and these charges are in square configuration, and then you can calculate the work in bringing these charges. So just read the problem and then analyze it. So for a continuous charge distribution, look at this. If you go back, this is just, so your V, this is the potential that is present in the vicinity, and then you bring Qi. Qi will just be for continuous distribution. The summation here will just become in an integral, and Qi becomes Q dq. Oh no, sorry, dq. I mean, this is wrong. This is dq. The integral, the summation Qi would just become dq, integral of dq. So what happens is that so if you have a charge distribution, dq will just be equal, for a volume charge distribution, rho d tau, or dq will just be sigma dA, or dq will just be, for a linear distribution, lambda dl. So for that, you will have in general, for a volume charge distribution, you will have 1/2. This is 1/2 rho. The rho d tau here is your integral dq. Integral rho d tau is integral dq. So that your expression for continuous charge distribution is is work equals to 1/2 integral of rho v, or the electric potential d tau. But if you have a line distribution, you use this. And if you have an area or a surface charge distribution, you use that. So here, let's continue. In the differential form of the Gauss law, this is what we have. This one here. And so if you replace rho in this in this expression, you will have, or you will get this expression. You will get that expression for the work done. So it's just a matter of playing with the laws of electrodynamics and then changing, replacing, and then you will have a new expression, completely new expression for the work done. So this is now the new expression. So if you do integration by parts, like what we discussed in chapter 1, you will be able to convert this into this expression, here. That's integration by parts, applying the Stokes theorem, and then applying the Gauss theorem. So you have that. So now your gradient of V is just equal to E, so therefore you can further rewrite the equation to be like this: epsilon sub over 2 integral of E squared d tau plus VE dot dA. So you just integrate over the region where the charge is located. Of course, it's an integral that integrates the charge. So whenever there is a charge enclosed, then you get some result. But if there's no charge enclosed, then of course the work done would be 0 because of the Gauss law. So there's a note here. I will just read it. But actually any larger volume would do, because you are just integrating over, you're integrating on the charge distribution. So whenever you integrate in a small volume or in a large volume that encloses the charge, it doesn't matter. So any larger volume would do just as well, since the extra territory will contribute nothing to the integral anyway, since the charge distribution is equal to 0 in the other region. You're only integrating the region where you the region in consideration where the charge distribution is. So in this case, the integral of E only increase. This will increase because the volume, if you integrate a bigger volume, the volume here is big, and so the E squared there, the integral of E squared d tau is bigger. But what happens here? If your volume is big, and so R goes to infinity, this potential, electric potential, becomes smaller at bigger volume, and also the E becomes smaller. So if this term will increase, this term will decrease, so that the work is still constant if you add them. So what happens? Okay. So that's the essence of it. Now, if you get the integral of this, if you consider the whole space or the whole universe, if you consider the whole universe, then you take this as all space, this one as all space, and then you have this integral. So all space that includes r going to infinity. At infinity, this one, you are integrating at the surface of infinity. V is equal to 0 and also E is equal to 0. So what happens? This will go out of the question. So what happens is that your work will just be equal to, in other words, wait, let's have you take screenshots of the slides. So your work will be equal to this if you integrate all space. This means that the limit of integration is, or for example for r, it's like from r to infinity if you take all space. So let's do an example. Here, find the energy, example 2.8. Find the energy of a uniformly charged spherical shell of total charge Q and radius r. So if you use this formula, so you get the potential caused by the surface, by the sphere. So the energy of a uniformly charged spherical shell. So you have a uniformly charged spherical shell that has sigma. So you use this as your dq, sigma dA, integral of sigma dA. But what is the potential? So you're just integrating what is the potential on Q? This is just the potential. I mean the potential experienced by the dq would be 1 over 4 pi epsilon sub O Q over R. And so you substitute this to here, and then you work out the integration. So everything will just be constants. So you're only be left with sigma dA. But again, your sigma dA is the dq, and the integral of dq is just q. So your work, so this is just now q squared. So your work will just be that expression. So how about we try another method? We try this method. We use equation 2.45, which is this. We use this this one. We integrate the electric field square of that over all space, and then let's see if we get the same answer. So we do that here. So the electric field is 0 inside the sphere. Why? Because inside the sphere there's no charge enclosed by the Gaussian surface, and therefore the electric field there is 0. So if you take the square, if you take the square there, that's 0 square is also 0. So that means it means that you don't have any stored energy inside the uniformly charged sphere because you don't enclose a charge there. But how about outside the sphere? Outside the sphere, you have an electric field. And the electric field is just given by this. And so if there's a field, then there must be an energy. So outside the sphere, you feel the energy of the sphere. But inside, because there's no field, you don't feel the energy, or you don't have the energy there. So if you take the square of that, that's just q square over 4 pi epsilon sub o square r to the fourth. And so if you do the integration, you just so you are in here, you are integrating over the in this case the whole volume, and the whole volume will just be this expression here. This is your d tau for spherical coordinates, because of course E is in radial, you have to use the spherical coordinates. So you will have the same. If you manipulate everything, you will have the same answer. Sorry. So that's the same answer there. This is the same answer. So whichever formula that you use will just give you the same answer. So there are problems here which you can solve. So you can take the screenshot of that. Then I'll leave you this slide, comments on electrostatic energy. Summarize it when we do the assessment of this lecture. I will ask you to summarize these comments on electrostatic energy. So just screenshot and read, then you have that also. Here's an important question here. Where is the energy stored? So there are two ways. So when you are so for example, it's when you look at the formula, you are integrating the square of the electric field. So when there is electric field, the energy is stored in the electric field. But the charge is causing the electric field. So the energy could also be stored when there is a presence of charge. So it depends on the situation. So you read this and then make an imagination and realize how things work in the universe. So anyway, the superposition principle. Thus, the superposition principle works in the getting the work of assembling the charge. Yes or no? Actually, no. It does not obey a superposition principle. It does not obey the superposition principle, because if, for example, you have two charges giving you an electric field, and the other one giving you an electric field. So if you square them, you get this expression, E1 square E2 square, and then you have E2 E1 dot E2. There is a cross term here, so it's okay, it will obey superposition if this is equal to just E1 square plus E2 square, but it's not, so it doesn't obey the superposition principle. So you can do this problem here, 2.34, screenshot it. So let's now go to conductors. What are conductors? What are insulators? What are conductors? You have insulators like plastics, for example. But I'm talking about ordinary plastics. So you have an insulator or a ceramic, for example. You have as the atoms in the insulator does not give free electron. It doesn't have free electron. So all the electrons in the atoms of an insulator stays in the atom. It does not go out of the atom. There are materials, especially metals, and these metals have free electrons. This means that the molecules of the metals give out electrons, free electrons, valence electrons that can transfer from one atom to another. So the charges in the metals can move. The electrons can move from one region to another because they have free electrons. But in an insulator, all the electrons are attached to the atom. A perfect conductor is a material containing an unlimited supply of completely free charges. But in real life, there's no perfect conductors. But many substances like gold, copper, silver, those metals are almost perfect conductors. There is a definition of a conductor. The electric field inside a conductor is always zero. It's zero inside a conductor. Why are you asking? Why? If you're asking why, so this is this case. When you touch a metal, it does not electrocute you because the charges, because there's no charge, there's no motion of charge. But if there's electric field inside a conductor, then there will be motion of charge, whether the electric field is outside or inside a conductor. There is motion of charge, and if there's a presence of electric field, of course inside a conductor it would be zero. But when you have an electric field that's on the space, and then of course it will disturb your conductor, and then I'm sorry, the electric field inside a conductor is always zero. And so if you have an electric field outside a conductor, it will disturb the conductor from the outside, and then the charges, since there are free electrons, the charges will reorient. And when you have reorientation of charge, there will be motion of charge and there will be current. So like for example, if when the moment when lightning strikes, the charges will already flow through the environment that you are for example, it's in this situation, when lightning is about to strike, the charges in the air will move, and then it will cause some electric field, some distortions of electric field in the environment. And so if you touch a metal before lightning strikes, you will get static electricity, because you will feel the motion of the charges on the metals. That's why it's you sometimes, if you touch some things like the front of the TV, because there are radiations, so radiations are like their motions of charges also. And then when you touch a TV, you feel some electrostatic or statics, or some charges there. And when you touch the metal during lightning, some of the charges are moving in the metal, so when you touch them, it's like biting you. So that's the explanation to that. By the way, in molecules, only the negative charges moves. And so but the total charge of the material is always zero. I mean, the total negative charge is compensated by the positive charge. So if you have a metal and then you subject it to electric field, the electric field will realign the charges so that it follows the direction of the electric field. And then you have now a rearrangement of charge. So some of the charges, the negative charges, will concentrate on the other side, and then the positive charges will also concentrate on the other side, but still the sum would be zero. So that's the conductor here. In this figure, looking at this, you have an electric field going in this direction. So it's what happens inside a conductor is that it will rearrange its charges. So the positive charge will come to this side, and then the negative charge will come to this side, the direction of the electric field outside. And so it will create an electric field inside, because there are now an imbalance of the distribution of charge. And by the way, this is important. The whole process is practically instantaneous. It happens very fast. Like when electron flows through the wire, the moment you plug into the outlet, electron moves almost instantly. So the arrangement will be instantaneous. When you plug in the wire in the outlet, it will create electric field inside the metal, and so the charges will move to the appliance, and the appliance eats it. And yeah, that's why now the appliance or the gadget will give out some tune, some light, that's how it works. And okay, again, because there's no electric field inside a conductor, the charge distribution there is zero. So whatever Gaussian surface that you draw inside a conductor is always it always does not enclose charge, or the sum of the charges that it encloses is zero. So there is still presence of positive and negative charges, but their sum is always zero. any net charge, this is very important, any net charge resides only on the surface of the conductor. That's very important. There's no charge inside. I mean, the total charge inside is equal to 0, but the net charge will only reside outside the conductor. So that's why when you touch a metal, sometimes you will feel that it bites you because of the charges that is present at the surface. And also, a conductor is an equipotential. This is also very important. Conductor is an equipotential. So if you go from one point to another point in a conductor, it's 0. Why? Because looking at this formula, the electric field is always 0. So the integral of 0 is just equal to 0. So therefore, your potential difference is 0, and so the surface is an equipotential, meaning the potential at any point is equal. There is potential, but the potential difference is 0. And also here is very important also. The electric field is perpendicular. The electric field is perpendicular to the surface just outside the conductor. Look at this figure. So here, all the electric fields are perpendicular to the surface. Whatever the shape of the conductor is, all the electric field at the surface are perpendicular. So you have here perpendicular, everything. I mean, in all the points in the surface, the electric field is perpendicular. The excess charges in a conductor will spread out evenly on the surface of the conductor. So this is what I'm talking about earlier, that there is an induced charge. There is an induced charge when the conductor experiences a field from outside. Say, for example, you have a charge here. This charge will give out electric field. So the electric field will disturb the charges of the conductor, and if this charge is positive Q, then it will attract the negative charges here, and so it will make a distribution on this side. The positive charges will concentrate on the other side. Actually, the positive charges doesn't move, only the negative charges moves. But since the electrons are here, it will give a net positive charge on this side. Okay. So you can read the text there. Then so now let's look at this figure. Let's look at this. You have this kind of conductor. It's in irregular shape, and then there's a cavity inside. So what happens here? The electric field in the cavity is not 0. As I've said, if you have a charge near the surface of the conductor, if this charge is positive, if this one is positive, then there will be a concentration of charge here. There will be a concentration of charge in this surface. What happens is that this charge here will the charge Q here will appear on the surface. That is the excess charge of the conductor. So anyway, what happens inside the conductor? Look at here. There's no electric field here. Always at the inside, at the interior of the conductor, there is no electric field. But here there is an electric field, and of course outside there is an electric field. There exists an electric field outside, because if you draw a Gaussian surface here, there will be a charge enclosed, so there's an electric field. So anyway, in the inside the conductor, if you draw an electric field, if you draw a Gaussian surface here, the Gaussian surface here, if you draw a Gaussian surface, it will enclose Q and the inner charge, which is negative Q. So the total charge you enclose is equal to 0. So therefore, the electric field is equal to 0 here. Okay. There's an important statement here. No external fields penetrate the conductor. Why? Because since they are cancelled at the outer surface by the induced charge there. And similarly, the field due to the charges within the cavity is killed off for all exterior points by the induced charge on the inner surface. So it's the electric field here is 0, because the electric field that Q gives off is killed off by these negative charges. So that's how it is. So you can read the text here. It's just what I'm talking about. So let's do an example. Here, example 2.9. An uncharged spherical conductor centered at the origin has a cavity of some weird shape carved out of it. Somewhere within the cavity is a charge Q. Question: what is the field outside the sphere? Here you have a charge Q, and so the inner surface here, the interior surface, will produce a charge distribution which is equal to negative Q. The negative Q will in effect make a charge distribution here, which is positive Q. The positive Q will be here. So when you draw a Gaussian surface outside, you will enclose a charge here that's equivalent to Q. And then there is electric field, of course, because you have an enclosed charge. So what is that electric field? So here, at first glance, it would appear that there is so at first glance it would appear that the answer depends on the shape of the cavity, but no, there's no way to be able to know if the shape inside the conductor unless you break the conductor. But if you don't break it, you will never know what's the shape of the cavity is. What happens is that you will just measure the electric field outside the sphere by this formula, regardless of the shape of the cavity. So you only calculate that the conductor conceals all information concerning the nature of the cavity. You will not know. So since the cavity has a charge Q inside it, it will induce negative charge on the inner surface, and the outer surface would be, of course, positive Q to cancel the negative Q induced in the inner surface. So what happens is that since the conductor carries no charge, no net charge, this leaves positive Q to distribute itself uniformly over the surface of the sphere. Okay. So you can read this slide, then go further. I'm just talking about the same thing. You can read that. That's just the details of these things. So now you can look at this problem, probably solve this problem. You can find this problem commonly in the internet, and then just spend time to be able to know them and to be able to know how to solve them. And of course, in doing so, you will learn. It's the most important thing. What happens here? Sorry for that. So that ends our session, the lecture, and probably the next lecture will be the last for this chapter. The next lecture, and then we'll start with chapter 3. So class, I will be giving out the assessment in a while, and then so the assessment would comprise the lectures that I have done today and the past days. So it will be very long. So but take your time, because you will pass this on next week, Friday. So oh no, not Friday, but Thursday next week. That's 1 week, or maybe, well, maybe Monday, I don't know, but just do it. See you in the next lecture.